All right, so because I will not be able to be in class this week, we're gonna, or not the week, sorry, just this Monday. Don't get too excited. I'm gonna continue the lecture on section 4.7, and let me go ahead and get some ink ready. So, section 4.7, which is Cauchy-Euler equations, we'll just continue that on the line. Usually I don't like to do this, but it is kind of a necessity just this Monday because I have a meeting at district. Now, if you recall, a Cauchy-Euler equation is an equation of the form uh, a sub n times x to the nth power and then the nth derivative of y plus a sub n minus 1 the n minus first derivative, and then, or sorry, x and n minus first power, and then the n minus first derivative, and so on and so forth down the line. So it's basically a differential equation with sort of like constant coefficients, except they're not, right? They're all polynomial coefficients, but the powers of those polynomial coefficients are the same as the degree or the order of the derivative. So it goes all the way down to a1 x to the first y prime plus a naught x to the 0th y, and it is equal to, in general, some function g of x. That's Cauchy-Euler. And we made a statement last class that all solutions to Cauchy-Euler's are of the form y equals x to the mth power, where m is a solution to the characteristic equation for the the Cauchy-Euler equation. And the characteristic equation for the Cauchy-Euler is much different, or maybe I should say slightly different, than the characteristic equation for a normal ordinary differential equation with constant coefficients. In fact, we were dealing with a Cauchy-Euler equation that was second order, so it looked like a sub 2x squared y double prime plus a sub 1 x y prime plus a sub 0 x to the 0th y is equal to, and we're just doing homogeneous second order ordinary differential equations Cauchy-Euler form. And we made the guess that y equals x to the m is the solution. And if that was the case, we got down to the following: x to the mth power, and you can check your notes for this, but we did get down to this: x to the nth power times, if you insert y equals x to the m into y, and then its derivative into y prime, and its second derivative into y double prime, you got the following: a sub 2 times m minus 1 plus a sub 1 times m times or plus a sub 0 is equal to 0. And if you look at this, this is a differential, I'm sorry, the solution to this, you could argue that x equals 0 is a solution, but x is not always going to equal 0, so we cannot just claim that x equals 0 is always going to be a solution. So the only way that we're actually going to always have a solution to this is if this stuff I've highlighted is always 0, and the only way we get that to be 0 is if a sub 2m squared plus, when you distribute through, a sub 1 minus a sub 2m, right? Because you distribute that a sub 2m through, and you get a negative a sub 2m. That's where that comes from. That comes from there. Plus a naught is equal to 0, and then we got all the way down to this solution. M is equal to the opposite of this middle term. Let me highlight that middle term really quick. The opposite of this guy, which just means I'm going to swap the order of the A2 and the A1. So it's the quantity A2 minus A1 instead of A1 minus A2, plus or minus the square root of that B term, which is A1 minus A2 quantity squared minus 4 times A2 times A naught. And now that gets kind of bulky, all over, by the way, 2a sub 2. And that was kind of bulky, so I decided to call this stuff right here in green, I decided to call that D. Actually, I'm just going to point an arrow at it and say we're going to call that D for the discriminant. Okay, so this is kind of a quick review of what we're doing. And what we did last time is we found out that if the discriminant is positive, it's a horrible positive, but if that discriminant is greater than 0, then we get two real solutions. We'll call them M1 and M2, but we get y sub c is going to be equal to C1x to the M1 plus C2x to the M2. In other words, we get two real roots. We'll call one of them M1, the other one M2. And this all came from the supposition that our solutions were of this form right here. So assuming our solutions are of that form, it turns out that the solution in the second order would end up being C1x the M1 plus C2x the M2. Now, if on the other hand, and this is where we left off, if that discriminant is 0, then we only have the a sub 2 minus a sub 1. Let me go ahead and write that. So if the discriminant was equal to 0, well, then we know the solution to the characteristic equation is, not them, then. We know the solution to the characteristic equation is m equals, and then the discriminant being 0 means that we have just a sub 2 minus a sub 1 all over 2a sub 2. And we did some work last time, and you can refer to your notes, but basically it came out to, we used reduction of order, so I'll say and using reduction of order, we get our first solution, which was the fact that we had at least one solution, this a2 minus a1 over 2a2. So we had one solution where it was c1 x to the m, but the second solution is going to be the natural log of x times x to the m. So in the past, when we've had constant coefficients and we'd have repeated roots, we would tack on, for example, and let me just move over to the side so I can recall with you. So in the past, if you had something like, oh, let's just quickly do this, y double prime plus 5y prime plus 6y is equal to 0. Let's just do that, right? And you get the characteristic equation m squared plus 5m plus 6, which factors down to m plus 2m plus 3 is equal to 0. You would get two solutions, -2 and -3, and so you knew your solution, your complementary function, or your solution to your homogeneous differential equation with constant coefficients, that guy right there. You know the solution is going to be c1 e to -2x plus c2 e to -3x. However, if instead you had y double prime plus 2y prime plus y is equal to 0, if you factor that down in its characteristic form, you get this, m plus 1 quantity squared is equal to 0. And we knew that -1 is a solution, repeated root though, so the complementary function would be c1 e to the -x plus, and then again, these constant coefficient ones, we'd have to tack on an x, and then e to the -x. Well, that's not going to work with Cauchy-Euler equations, because tacking on another value of x right here is just going to raise the power of this exponent by 1, and that's a problem because then it's going to imply we have a root to our characteristic equation other than m, and that's not true. We only have m as a root to our characteristic equation, so it's just why that works. So now let's go ahead and move on. I had to check which example number we were on. When we were in class, we left off with that was example 1c. So we're going to do example 1d here. And that is really the question, and I should probably keep with the same coloring on my ink here as I do in class, or as I try to do in class. Example 1d. Okay. What if the discriminant is negative? In other words, when I scroll up here, the stuff in green that I've highlighted, what if that's negative? In other words, we have imaginary solutions, well, to our characteristic equation. Well, if that's the case, and I'll draw out my work in blue here, if that's the case, well, that will imply that the value of m is equal to some real part, which is technically speaking a sub 2 minus a sub 1 over 2a sub 2, plus or minus some imaginary part, which again, technically speaking, is square root of d over 2a sub 2. But remember, d is negative. But all of that, I could care less about the notation there. I just want to write as alpha plus or minus beta I, right? Because once you take that square root, you get an I out of that if there was a negative in there. Well, if that's the case, we know that our two solutions are going to be x to the alpha plus beta I and x to the alpha minus beta I. So let me go ahead and write that in here. This implies that our solution, or complementary function, a solution to the homogeneous version of this Cauchy-Euler, is going to be some constant, x to the alpha plus beta I, and then some other constant, x to the alpha minus beta I. And you notice that both those have x to the alpha in common, so I'm going to factor out an x to the alpha. And when I do that, I'm left with C1 x to the beta I plus C2 x to the negative beta I. And we're going to use a little trick here. We're going to raise, since we know that e to a natural log of y, let's pretend, is equal to y, what I'm going to do is rewrite each of those expressions, these x to the beta i's right here, as e to the natural log of x to the beta i's. So I'm really not going to change them. I'm just going to change the look of them, but it actually won't change them computationally. So I'll say this is equal to, let's scroll over a little bit so that we can keep on the same page. Oops, that's too much probably. X to the alpha, and I'll have parentheses in here, so I'm going to create a little bracket. E to the natural log of x to the beta I. It's a little trick we do in mathematics every now and again. Plus C2, again, e raised to the natural log of a negative, or not negative yet, the exponent's negative, x, sorry about that, I'm left-handed, so whenever my hand hits my screen, not whenever, but often when it hits the screen, things shift, so sorry about that, but we get this. And now you know those exponents can be pulled out front, so let's go ahead and do that. It's my left hand knocking things down. X to the alpha, quantity C1, e to the beta I natural log of x, and plus C2 e to the negative beta I natural log of x. Oops, and close off that in parenthesis. Now, this should be somewhat familiar. We did something in the past. I want to say it's like section 4.2, where we, in fact, maybe I could find it really quickly. It took a while for me to find it there, but it's 4.3. A lemma right after we learned Euler's formula that if you have two solutions, e to the alpha plus I beta x and e to the alpha minus I beta x, then we can combine them, right? And so really what this is saying is if you have e to the I beta x and e to the negative I beta x, you can rewrite it as a cosine of beta x and a sine beta x. And that's exactly what we're going to do here. So getting back to our formula, we're going to just trade out those e to the beta natural log i's, natural log of x times i's, and e to negative beta natural log of x i's for cosines and sines. And remember, it takes pretty much everything except for the I. So this is going to equal x to the alpha times the quantity. It's not really going to be the same constant. It's going to be a different constant. But d1 cosine of beta natural log of x, because that is the coefficient of I, plus d2, darn it, my left hand is just touching the screen, plus d2 sine, again, of beta natural log of x. The derivation of this is identical to the derivation of the formula in section 4.3. That's where we actually ran into it. So now we have actually all the possibilities for when we are solving a Cauchy-Euler differential equation, at least the second order. But as we know from the fundamental theorem of algebra, all polynomials, which is what the characteristic equation is going to be, all polynomials can be factored down into linear and irreducible quadratic factors. And then we can go ahead and use our newfound theorems to help us out. So let me just repeat or write down those as a theorem. I'll just, since blue I usually use for theorems, I'll just do that. Theorem given, let's see, it's a sub 2x squared y double prime plus a sub 1 x y prime plus a naught y is equal to 0. And noting that d is equal to the discriminant of the characteristic equation, and the discriminant of the characteristic equation is going to be the quantity, darn it, that's my left hand again, the quantity, I think it's a2 minus a1, or a1 minus a2, that's where it is. So d is equal to a1, it doesn't really matter when you square it, it becomes the same thing, but squared minus 4a2 a naught. Okay. The solution is y sub c is equal to c1 x to the m1 plus c2 x to the m2 if d is positive. In other words, we solve the characteristic equation, and that's the form of it. Otherwise, it is, let me dot these out, c1 x to the m plus c2 natural log of x, x to the m, if the discriminant is 0. Again, the discriminant of the characteristic equation for the Cauchy-Euler. And by the way, we don't often compute the characteristic, honestly. We just kind of barrel through and do it. But so far, so good. And finally, y sub c is going to equal to e to the, I have to actually give myself a little more room here. I should be using actually a different size paper. Y sub c is equal to x to the alpha times the quantity c1 cosine of beta natural log of x plus c2 sine of, again, beta natural log of x. And that is if the discriminant was negative, because we end up having imaginary solutions. That's where the alpha and the beta come from. Now we can pull all this together to start solving Cauchy-Euler differential equations. And that's exactly what we're going to do, but I'm going to maybe stop this video so that each of the videos is kind of nice and short, or shorter, and then we'll have a video for each example. Okay.